Welcome to Math Superville. In this video, we're going to discuss examples relating to sigma notation. So in the last video, I discussed the concept of sigma notation and gave you the rules that govern sigma notation. I referred those rules as properties of sigma notation. So let's look at some examples of sigma notation. So example number one. Expand So number one, expand this summation. So here I'm going to ask you to expand I plus 10. And our index runs from 1 through, let's say, 4. So the solution in this case, remember the rule for summation, which we call the sum and difference rule. If you don't remember that rule, then I will refer you to the previous video so that it can guide you on how we should attack this problem. So according to the sum rule, we can split the sum, which is I plus 10, into two summations. The sum of I with the index running from 1 to 4 plus the sum of 10 with the index running from 1 through 4. And if you remember, the sum of I was n times n plus 1 divided by 2. And then the sum of a constant was the constant times n. So if you should remember this rule. This was the rule that we talked about in the last section. So next, I'm just going to replace. So our n is 4. So that means the sum will be 4 times 4 plus 1 divided by 2 plus 10 times 4. And that gives you 20 divided by 2, which is 10 plus 40, and the answer is 50. So that is the first example. The second example is this: expand so we're going to expand I cubed plus 3i with the index being lower index as 1 and upper index as 10. So in this case, our solution will involve applying the properties of summation that we talked about. So that means our summation I cubed plus 3i with the index running from 1 through 10. This will require the sum rule and the constant multiple rule. So we can split the sum to be I cubed plus the sum of 3i with our indices running from 1 through 10. And if we continue, this is the same as the sum of I cube with the lower index as 1, upper index as 10. Now the next one, we're going to use the constant multiple rule. So that entails factoring out the constant and then multiplying that constant by the sum of I with the index running from lower index as 1 and upper index as 10. Now, if you remember from our last video, the sum of I cube from I is equal to 1 to n is n times n plus 1 divided by 2, and then you square that quantity. So that was the rule. Of course, we already talked about the sum of I with the index running from 1 to n, and this gives us n multiplied by n plus 1 divided by 2. So the first quantity is the sum of I cube. So in our case, n is 10. So the answer will be 10 times 10 plus 1 divided by 2 square. The next one is 3 times the sum of I. So n is 10, so that's 10 times 10 plus 1 divided by 2. So the next thing is to just simplify this. So this is 5 times 11 squared plus 3 times 5 times 11. And when you put this in your calculator, your final result should be 55 squared is 3025 plus 15 times 11, 165. So 3025 plus 165, that gives us our final result as 3190. So, and these are examples relating to how we can apply the concept of sigma notation. All of the other rules that we have discussed, as you can see, they come in very, very handy whenever you are discussing how to solve some of these problems. In some situations, you will be required to condense a sum, an expanded sum. So let's look at that. Express one plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128 in sigma notation. So this is example 3. So the solution entails looking at exactly what's going on. So notice that you are sort of summing squares. it's not squares, but 2 raised to some power. So you will notice that this is 2 raised to 0 plus 2 raised to 1 plus 2 raised to 2 plus 2 raised to 3 plus 2 raised to 4 plus 2 raised to 5 plus 2 raised to 6 plus 2 raised to 7. In fact, if you notice, each of these match. You can put each of these into your calculator and you'll realize they are correct. They are the same. So how many quantities are we summing up? 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 quantities, and the lower index, I will use the exponents as our indices. So I will say our I goes from 0 to 7, and we are summing 2 to the power of I. So you could think of each of this as your I. When I is 0, you end up with the first one. When I is 1, you end up with the second one. When I is 2, you get to the third one, and then the fourth one, and then the fifth one, all the way to the seventh one. When you get to the exponent of 7, you have reached your upper index of summation of this sum. And therefore, we are able to condense our summation accordingly. We could also rewrite this as the sum from I is equal to 1 to 8 of 2 raised to I minus 1. So that when I is 1, notice that you still have the same result. So we can actually try to modify what we're doing, and it will still work. So I challenge you to actually look at exactly what I just did. So the indices of summation can be modified accordingly depending on what is required of you. If you have to begin with an index of 1, then you have to express your result accordingly. So these are some of the examples I can give you. Feel free to explore more. As you can see, we can condense and we can expand any summation as discussed in this sigma notation video. Thank you. I hope you liked it. I hope you liked this video. Try to subscribe, comment, and continue to follow us. Mab Subabil.